Hello, everybody. Thank you for joining us for today's LJC event with Dennis. Let me introduce myself first of all. My name is Abby and I work with the LJC and the 15 plus other communities, all of which are free and run by RecWorks. We are a tech recruitment company with a difference. As a company, we're always on the lookout for more clients, and some of our best clients have come from community members who've recommended RecWorks to their internal talent teams. So if you are hiring for a new team or you're working for a company that is, please do let us know. And if you want to know more about what we can offer, ping me a message on Twitter, LinkedIn or Slack. My name is as you see it on the screen, and we really look forward to having that conversation and working with you. So what's the difference, I hear you ask? Well, also as a company, we believe that recruitment really can be a force for good in the industry beyond just placing people in jobs. We have a particular focus on learning, mentoring and personal development, and that is where all of our events and communities come in. If people want to learn and others want to share their knowledge, we are more than happy to connect you through our communities and events. We see this as giving back to those we've worked with in the past, but also paying it forward to those we hope to work with in the future. To date, we have run hundreds of different events for engineers, developers, students, graduates and CTOs. We have run conferences, lightning talks, hackathons, all sorts. Earlier this year, we made our 4,000th introduction through our Meet a Mentor community. That does what it says on the tin. And we're really excited about making our 5,000th introduction through that community. As I've already said, we love to give opportunities for people to connect, and this event is part of that. If you'd like to know more about any of our communities, please do, again, get in touch with me on Slack, LinkedIn or Twitter, and we can go from there. If you are already part of one of our other communities and you know Helen Lewis or Barry Cranford, then also you can get in touch with them and they can refer you on to the right community as well. The recording of today's session will be available for you on YouTube. I will put the link to the channel in the chat for you later on. And if you have any questions as Dennis is speaking, please do make a little note or you can put them in the chat, and then we will have a Q&A session at the end. There will be an opportunity for any questions you've got. So be thinking and just make a little note. That would be great. With no further ado, though, let me hand over to Dennis. Over to you.
Thank you so much. Greetings, my name is Dennis McCogan. Thank you for having me here at the LC Job. My name is Dennis McCogan. I'm a principal member of the technical staff and a Java advocate at Oracle. I'm also practicing the cloud solution architect, a Java developer by nature, and the open source fan. Probably we have met at one of the conferences that mentioned here on the screen, but it's a bit of like a self-pitching. Today I'd like to talk about building Java applications with native code using Project Panama. For quite a while, you know that Java developers have been using technology called Java Native Interface, or shortened JNI. It allowed to bring native code to Java applications. The fact that this feature exists is already kind of an advantage, but let's take a closer look at it. First and foremost advantage of the JNI is that it allowed to bring native libraries and tools that either weren't available in Java ecosystem nor possible to be implemented in pure Java. The second, it doesn't matter would that be C or C++. The only requirement is to follow the exact contract generated by Java H code, the CLI tool, which is a part of the JDK 8. But with the later JDKs, it was removed in favor of the specific flag for Java compiler. However, all of these benefits, it comes with a particular cost. Now in 2022, we can and have a moral right to talk about JNI disadvantages. The power and the weakness of is that the code that you write with the JNI is platform specific. Unexpected errors in native code can literally like crash JVM. No viable debugging process. I'm kind of referring to the good old print statement debugging that you use to debug code that exists in the native stack and then inside of a JVM. Even though all these potential problems with the JNI, they exist, but the JDK, if you have ever looked inside of the source code, is full of that. But, which means that this technology was battle tested in production by many developers, and people who are responsible for that are very smart, very talented engineers, and also the scientists. As I was preparing for this talk, I had a conversation with Mauricio Simadamor, who's Project Panama lead and probably the most well-known native code in Java spokesperson. So certain changes that will happen to the APIs, I will cover today. But if you want to read in advance, you can scan the QR code, or just go on Reddit and search for dissecting memory sessions. So the purpose of Project Panama is to change the way developers interact with the native code from inside of Java applications. In this talk, I'll try to cover almost everything: foreign functions, memory API, a new JDK code generating tool called JExtract, and vector APIs as a cherry on top of this very tasty cake. So foreign function and memory API offer a variety of new APIs that attempt to give you an answer to the following question: how to invoke a native function of a particular signature by its name. Every of these highlighted words correspond to a particular API class that is a member of foreign functions and memory APIs. So let's start with a linker. Linker, in terms of computer science, is an implementation of a C application binary interface, or in short, ABI, which sounds similar to API, but it's a binary. The purpose of the linker is to provide the necessary capabilities to perform both down calls from high-level system to the lower-level system, and the up calls is the opposite direction. For instance, invoking C code from the JVM is a down call, and obviously a call to the Java function from C is the up call. So linker implementation that is available right now in JDK supports almost every popular platforms on Windows, Linux, and macOS, including AMD 64 and ARM architecture processors, which actually this demo is running right now. While linker answers to a question how to call a function that you have, a symbol lookup is more of about to find a function by providing an interface for searching an address of a function by its name. So basically, if you have used application binary interface before, you know that the kernel is capable to search in a shared library a native symbol by just having its name without even having its signature. So that's what the symbol lookup, or that's what that is in Java, and that's how it also works in Java. You give it a library either through the JVM command line arguments, or through through the system properties in the setup from code. At the same time, symbol lookup gives an answer to where the function is located, but it doesn't give you any hint what kind of function that is. So no type being associated. So there's no type associated with that function. So the function descriptor APIs is kind of the way to describe what type of a function we'd like to invoke by describing a signature of that function that consists of a return value, of positional and variadic arguments. So that's what kind of represent the signature of a function that is you create when writing the C code or Java code. It doesn't matter. You just have different terms in different languages. Similarly to JVM, that has no idea what the type of native function it will invoke. C has no idea what type of a function, what type of types Java has. So when Java apps crosses the border between by stepping into the world of native code, it has to explain to C what the data it is passing back and forth between the JVM and the native code. That's why foreign function memory API offer a set of valuable layouts to sketch out off-heap memory persistence that can help identify by the C code. So basically, value layouts, group layouts, struct layouts. These are the classes that for the Project Panama offers you to basically describe a type of a variable that will be passed back and forth between Java code and native code. So for instance, C has structures, group layout class will help you to sketch out the struct. You can also have a different C native types that can be described in Java. It helps the JVM and the C code to basically work with the values by describing their types in form of like of a Java object. So instead of following the same programming model with as with the JNI, you see the foreign function memory API provide you different angle of view to the native code invocation. For instance, foreign function and memory API provide method handles, which is not a new thing to the JVM. It existed for some time ago, and the whole reflection framework is using method handles to provide executable objects for Java methods, and gives you an like, let's call it like a reflective access to objects you're working with. So the method handles, foreign function memory APIs give you a method handles as a strongly typed, directly executable objects bound to the native symbol, constructed from the address of a function that being identified through the symbol lookup, and the function descriptor that you create to describe what kind of a function you will invoke. So the function descriptor, like it's a new type of a resort that tells the JVM what the meta type a method handle must have in order to comply with the original C function signature. So you see that you're using the linker, the symbol lookup, and the function descriptor. These are basically the building blocks that helps you to create a down calls to the particular function and describe data types that aren't specific to Java but are defined in C. That includes pointers, primitive types like int, short, char, and etc. This what helps the JVM identify what kind of data is being stored in memory segments that will be allocated on off-heap, that will allow the native code to access that memory through the pointers to that memory, which is also can be identified can be communicated back to Java to let it access to a variable or to an array using the C pointer, which is kind of help. So both method handles and var handles that aren't new to, as I told you, aren't new to Java ecosystem or the JDK. These classes form a skeleton of the JDK reflection framework. They designed to provide an access to Java method handles and class attributes, no matter what kind of access mode they were defined with. Before Project Panama, we had to work with Java native method. So the JVM was responsible for creating a harness between C function and Java method. But now developers will be responsible for creating optimized method handles by providing effective constants for a linker, for a method handle, for a function descriptor, and the result of the symbol lookup, which is the memory segment type. And all of that form a very effective form of interacting interaction between JVM and the native code. More interesting concept is an up call. While a down call, as I described before, allow you to invoke some native code, the up call allow you a lower level system like C to invoke Java code. So in C, we don't have like a function type because it's not C++ where you have specific class that we call function. However, we can create a pointer that can correspond to one or many C functions that can be invoked through that. So similarly to down calls, using linker, we can construct a pointer to Java method through the method handle, mapped to a pointer residing on off-heap memory. That memory address, so the address of the memory segment stored on off-heap is what a C function can use as a function pointer to invoke Java method. It doesn't seem complex. Well, it might be, but it actually not. The biggest question is probably the most important one is how to manage an off-heap memory within the JVM. So you see almost every aspect of writing Java application that use native code is somehow bound to native or off-heap memory management. If some of you have worked with the JNI before, you know that there was a need to properly manage memory on the C side, on the native code side, in the same way, because the JNI was mostly C or C++ code, so you have to deal with C standard library functions like malloc, calloc, and realloc, which isn't a thing for the Project Panama, as it offers a way to deallocate memory segments once they no longer needed. Thanks to the very powerful and blazingly fast garbage collector. At the same time, developers can use more advanced memory allocation techniques using memory allocator that allow you to allocate the memory arenas. So it's a large fixed piece of a memory. Note that term arena isn't Java specific at all. It actually came from C++. And if you have worked with the protobuf and have ever looked into that implementation, you probably noticed that when you receive like a stack of the data, a library allocates a piece of memory that basically fits the incoming data. And then basically, and the rest of the code will just do the management within that segment. But when that segment is no longer needed, it will be erased in one run instead of deallocating per value memory segments. So often these arenas used in a segment per task use cases. So by the end of which, the only thing that is necessary to do is to reclaim the whole segment in one go instead of, as I said, doing the per variable reclamation. So that's basically what the representation of segment allocator in general, how it in general works, and also in that way it also works in Java. So you see that segment allocator is kind of a lower level APIs that allow you to allocate to manage the memory, which isn't a replacement to a memory session, which is meant to be like the top level API class that you need in order to either start memory session or finish it. So the memory, it gives you a more flexible way to manage more granularly managed memory. But rather, so you see that the segment allocator isn't a replacement for memory session, but rather a way to manage the memory arena at once using the same allocation methods. So the memory session can do literally the same as the segment allocator, but can work against all available off-heap memory, while the segment allocator can often used to work with against arenas So through the segment allocator, you cannot work with the whole available memory on your machine, but it can work with a session that is within a started session. So you can allocate a segment of a memory and then tell to the segment allocator to basically operate only with this particular segment by providing the same API interface for allocating native types and native type memory segments. Like you can store value of native types and also arrays. After working some time with memory sessions and segment allocators, it appeared that a session object often being needed everywhere where we need to allocate off-heap objects. But having a memory session as a global state could be problematic as the whole app become kind of a fragile. So it means that if you will work closely with the foreign functional memory API, you will notice that you need to pass down a memory session as a parameter to every function that does allocation of the memory allocation. Which isn't very comfortable because the top level object is still fragile and still can be. So if like another thread will close that session, eventually all other allocations will no longer be successful. That's why there will be new APIs available in JDK 20, either in a preview or in incubated form. It's called Arena Sessions. So often, as I told you, that you need to pass down the memory sessions through your Java methods, but Arena session allow you to start a very tiny, short-lived memory session within, let's say, your function, by basically allowing you to simplify the function, the Java function signatures. So anytime you need an off-heap memory allocation, so there is no need to pass the memory session as a parameter, but instead you can use Arena that has its own session built in. So by itself, an Arena is kind of it's closable allocator, so you can use that within try with resources construction that is associated with a session. All segments allocated with the Arena session is associated with a session within that Arena. So when Arena is closed through either using the explicit or implicit form, using method close, the underlying session will be closed, thus invalidating all the segments associated with the memory Arena, which means that you can start the Arena within your function, within your Java method, and then just close it once you no longer need that, and then the memory will be reclaimed back to the rest of the off-heap memory by allowing other let's say Arenas to allocate that memory. And similarly to a memory session, Arena also has an access to the whole off-heap stack, which isn't a thing for the segment allocator. So it can work with the all memory available, but it doesn't guarantee that if you will try to allocate that amount of memory that isn't available in off-heap, you will probably see the error like out of memory, which will indicate that you're basically trying to get more than you allowed to do, which means the whole allocation kind of I would not say like a thread save, but it's definitely concurrent. So other threads can start the Arena and then ask a memory like all available memory, and the rest of the threads probably wouldn't be able to allocate more than that. So based on the implementation, a memory session always bound to a thread. That's why I mentioned the concurrency. So it was started. So the memory session is always bound to a thread where it was started, which isn't a thing for Arena. For instance, Arenas So for instance, the memorization is so whatever session you start, memory session you start, it basically will be unstructured, which means that isn't thread safe, and other different threads can ask for memory without. So that makes the whole memory session fragile and being not thread safe. So, but the concurrent arenas, structured arenas, they are thread safe, and they basically they can be closed at any time in the case of sharing. And in the case of sharing memory session, the other threads will still be available to allocate some memory segments using that arena. But you see, this kind of a code form is somewhat being inspired by structured concurrency that was introduced in JDK 19 as an incubating feature. So in JDK 12, we're probably gonna see, but I'm not saying like for 100%, but it's still under active work. So in JDK 20, we will JDK 20, sorry, will offer a new concept called structured arenas. So the term arena was borrowed from the original structured concurrency that is not specific to Java. It's a type of a concurrent work, the concurrent work in computer science. But in our case, it was inspired by structured concurrency that was implemented in the JDK within Project Loom that give you an access to a virtual threads in a form of a preview feature starting in JDK 19. So the structured arenas makes the current thread the only one who can close the arena, but it still can be, but still the arena that being shared within other threads can be accessed in order to allocate more memory segments, which but they are not able to do it more than that. Basically, they can allocate, but then they are not able to close the session from a thread which doesn't own the structured arena. So you see, there are like two different programming models nowadays. We have a pure C++ that involves cautious memory management, because it's very, so you know that those languages basically forces you to do a very thorough memory management. So and we have in Java, we have JNI, which is mostly also C and C++. So you still same problem. You still have some of the same problems with that came from C or C++. But with the JVM harness applied to that native code, which is still like a kind of a pure C code. So now we have Project Panama style, where developers taking more responsibility that was a thing in the previous ones with the pure C++, or with the JNI, meaning a developer will be responsible for creating the infrastructure code, making sure that the code is optimized and efficient. But there's one major change. In Java code, the developer has to do what C compiler does with the C code. You need to, using the linker, for the symbol lookup and the function descriptor, you need to create a compiled create a compiled approximate version of a function you'd like to call, and or the exact invocation layout for the C function. There is a major change in the whole in the experience you might not expect to have. But we aren't only the ones in this boat. So every programming language that decided to adopt C application binary interface concept forces developers to do exactly the same. So yeah, pretty much it. Anyways, the most interesting part in Project Panama is the linker. It actually acts like a C compiler in Java code. It compiles the invocation to native function with a bit of help of the JIT compiler. And let me explain this in a very details. Let's look at this at the simple C application. We all know that the variadic argument and the methods are in Java, but in C it's kind of a different type of a feature. In Java, variadic argument support is a runtime feature handled by the JVM. In C, it's a compiler time feature, so the variadic function exists only in a code text. At compile time, these functions turn into a specific variant of themselves, but with the exact arguments, argument types, order, and a quantity. So that's the responsibility of a developer will be to create all the steps that I described, but now in Java code, which leads to a creation of a specialized variants of the same variadic or a function that will basically match to the exact combination of variadic arguments, the type, order, and quantity, similarly to what the C compiler does. So you see that when you invoke variadic functions in C or C++, the compiler will take the responsibility of creating the exact invocation signature for your function, but it's not a thing for Java when we're talking about the native code invocation. You have to create the exact signature of a function that eventually will match to the invocation arguments. Otherwise, you will have that problem. But that's only one way of doing so. This kind of thing that you need to do isn't the downside of the C application binary interface, but something developers have to kind of live with. Therefore, developers responsible for not the invocations of the native functions, but for the rest of the components that make the native code invocation possible in Java code. So most important thing that in the infrastructure code, it basically consists of a linker, the symbol lookup, the method handles, function descriptors for each of the functions, the opcall configuration, etc., must be performance effective, which means all these components that I've described must be effective constant, which means static and final. So the JIT compiler can go and optimize that code as heavily as possible to make the further native code execution cheap for the runtime, especially when the invocation will become the function or a Java method that you invoke will become hot, and the execution time will significantly be optimized by the JIT compiler. So if it's not a thing, if your components are not effectively static and final, which means not constants, the JIT compiler optimization wouldn't be possible for dynamic code that makes the execution as expensive as with the JNI. So it's either a choice, you see, between the flexibility, which it gives you a parameter-based method handles when you define, when you have like a generic invocation signature, and then during the invocation, your code basically will recreate all the components that will correspond to the parameters you use to invoke a native function. But the good thing, and the other one is the performance-wise solution, where you have all the components as a constant. But there's a good thing is that the infrastructure code is mostly written once and not very often revisited. Just believe my experience. So it's kind of a choice between the performance. So in most cases, the performance-wise solution is more appreciated because it gives you, so your solution will basically be backed up by the JIT compiler optimizations. So you see, the only thing is that may require a developer to change the infrastructure code is unless like the underlying library has changed, and new APIs or modified APIs or new types being introduced, for instance. So to make life easier and much simpler for developers who work with native code, Project Panama offers a new and the first standalone JDK code generation tool, which is called JExtract. So JExtract isn't a part of the JDK distribution, and because the target audience isn't that wide, so like not many Java developers have ever spent a lot of time writing native code. But there are some tools that are available in Java, but they require, for some reason, you need to introduce them to your Java application. So whoever needs it, it will find a way to download the JExtract binary. So it's also interesting that JExtract isn't just a single binary executable, but a J-linked Java runtime that consists consists of all JDK modules with the addition of the JExtract module, which means that you get basically Java runtime that has a way to start JExtract. So eventually, if you're going to use JExtract, you will see that you're going to have two different. So that you wouldn't have like a single Java for your Java with a specific version for your application, but you have different runtimes, which means that if you need to build the JExtract using your own JDK version, let's say like for now you can get it on JDK 19, but if you want to go and try on JDK 20, you need to download that and then basically recompile it for your own needs based on the tools you based on JDK and CLang library that you're gonna work with that you used to work with. So what's this all about? JExtract can generate a Java package that will contain the infrastructure code for native symbols defined in a target C header. So basically, when you if you want to create, let's say, a package that will contain all, let's say, C STD standard library input-output library APIs, you can basically tell to JExtract that here's it pointed to a C STD IO, generate a packet for me, and the output to the particular basically packet and the location. And that's what will happen for you. So instead of writing tons of code that I described before, for instance, the function descriptor, linker, method handles, and etc., it could be done for you by JExtract. It offers a good level of code optimization because JExtract creates constants for method handles with one exception. Variadic arguments that I've showed you before with the cprintf function are exempt from this rule of being highly optimized, at least until the invocation of that function will become hot with a particular invocation parameters. Because JExtract tries to be a good fella and provide dynamic parameter-based solution to native variadic function, which so the JExtract will create like a custom array collecting variant of a method handle to a C function that you would like to invoke, and then we'll try to guess what are the carrier types of parameters used to invoke native code to reconstruct both function descriptor, method handle to match the parameters that you're invoking function with. So it's not kind of like the most effective way to do so. So if you're, if you're considering, but at the very beginning, when you want to work with the native code, you know exactly what are the parameters you're gonna work with. It's highly recommended to create effectively static variables to make sure that JExtract can do a better work for them on your for you. So such solution indeed works as expected, that the dynamic parameters. However, it makes the whole infrastructure code dynamic. Therefore, an invocation becomes way expensive, even if you do a fewer calls to those functions, because the solution is based on the fact that we need to guess what inside of the object array, I mean the object types, order, and the quantity that you use to invoke the underlying C native function. So you see that it's either you either agree with the less optimized variadic arguments, arguments and functions, but truly dynamic variadic arguments or heavily optimized JIT constants, but a very specific specialized method handle for each combination of positional and variadic arguments, which makes the whole code more efficient and less dynamic, which I already told you is something that JIT compiler will thank you for it. Okay, among deliverables, the Project Panama provide vector APIs as the so this concept isn't very specific to Java, but rather have its roots somewhere deep down in Intel, AMD, or ARM CPUs. What we don't really see in the CPUs that we work with perform the operations in the form of vectors of a specific types, signed or unsigned integers, floats, doubles, bytes, etc. In the context, the term operation stands for various arithmetical tasks like multiplication, adding, negating, or fuse, multiply, add. There is like a big catch when it comes to actually doing some code that involves vector operations, because each manufacturer, like Intel, like AMD, or Apple with its ARM cores, follow their own specs and release cycles, which means that the same code, like the one you see here on the screen, wouldn't work on all of them. For instance, it will work only on 2 of these 3, Intel and AMD, because both of them support 256-bit vector operations. Oh, and moreover, this code that sums to vectors using 512 bit intrinsics that will only work on the very specific Intel and AMD CPUs, but none of them will work on ARM processors, because they only support, as far as I can recall, 128-bit operations defined on ARM Neon architecture. There are a lot more limitations that may be specific to the architectures, but or be limited to a particular one. So first conclusion may seem like that the same code would work on all platforms, but only in case of C++ code, but not for Java. Taking into account the fact that vector intrinsics are platform specific, even though some of them shared among a few manufacturers like Intel and AMD, GDK gives you a better perspective to the given problem. You either let GDK figure out optimal vector bit length, or pick the exact one, and fall back to the optimal one if the longer vector versions are not supported. So, for instance, if you will do on macOS M1 chips or on any M architecture, the best you can get is, as I told you before, 128 bits per vector operation, not more than that. So if you're gonna try to use a longer version of the vector operations, your code eventually will fall back to 128 bits, which is the only thing that is available on ARM chips. But if you will use, let's say, 520 bits on the high-level Intel processors or AMD Ryzen 7000, you will see that all these processors will be capable to perform these operations. And when you probably, if you ever seen like any marketing operations, even those ones that came just right before the release of a new Intel chips, it often says that a new processor is like 2, 5, or 10 times faster than the previous one. It means that something has changed in Vector API, which allow you to do a more longer operations, which is kind of fun thing to look at, because eventually it may be only 2 or 3 times faster operations, but not more than that. So why and when do you need vector operations? So while the explicit application are pretty much obvious, like fast Fourier transformation used in any analog to digital signal transformation, but some areas are hidden away from us, like compilers that we work with. When you're getting familiar with the vector operations, loop auto optimization is the first thing you will encounter with. Often these loops are a good subject for further optimization, therefore could be processed in a distributed manner, thread or parallelism, or using vectors that impose a lower level, lower cost for the infrastructure around the specific operation. For instance, dot production as an example. So you see that vector operations is like always faster and always cheaper than the same attempts to do a distributed processing, as I mentioned, using platform threads or any kind of other parallelism. So the C2 compiler in Java isn't the exception here. It can do auto vectorization for your code. Before that, we obviously had a fewer ways to perform vector optimization operations, like through the JNI, or you can basically use C++ API that is provided by Intel that gives you an access to the operations that use vector intrinsics of a specific length. Before that, before the auto vectorization capabilities of the C2 compiler, we obviously had a way to do this through the JNI, through Java streams, but none of them was cheap or even optimal, because you're adding additional cost of the infrastructure around your code. For instance, you need to create additional threads. You need to manage the MapReduce stuff. You need to basically process in threads, then collect it back, and etc. The JNI is also, you need to write that in the C or C++ code, and then create a library which would be the platform specific stuff, and etc. So the Project Panama aimed to make vector APIs be that missing piece for the compiler to optimize the existing code with no changes needed. But there's a catch. So you have to be sure that your personal code that you write gives the best performance metrics. For these purposes, I highly recommend to use Java micro benchmark harness to make sure to measure time on the longer JVM runs to see if method become hot enough so the compiler make an attempt to optimize it. So the numbers you see right now on the screen, that basically represents 3 different operations. First is a native vector API using Project Panama, and the other one too is using explicit for loop, and the other one using parallel streams. You see that the amount of time being spent by, for instance, stream implementation of the 2-vector adding, it takes a lot more time than the other ones. But at the same time, for loop and the vector code, they basically sticking around the same time, which means that the C2 compiler was able to identify your for loop as the candidate for the optimizations. But if you want, so these numbers, the first one will give you by the Java micro benchmark harness. But if you will do some kind of like a synthetic test, which isn't a benchmark, which won't preheat your function or the JVM, you will see that for some reason your code potentially will be fragile, which indicates 2 things. First, something wrong with your code. The second thing, the way you test in your code isn't actually a performance test, because the for loop and the explicit vector APIs should give you the same time. And to prove my previous statement regarding auto-vectorization, here you can see an execution time over multiple executions within the same JVM instance through the significant period of time within the Java benchmark. So the approximate numbers you see here are the results of two things. First, auto-vectorization against for loop, and the compiler optimization. So you see that at the very beginning, the amount of time being spent in order to execute a function was kind of a lot of time being spent. But with more and more times for executing this function and becoming hot, this is what the compiler does by reducing the time for the execution, which also called hot function. Okay, let's wrap up with the technical part and talk a bit about Project Panama in production. First, who already using Project Panama? These are three projects that doesn't require any introduction: Netty, Tomcat, and Apache Lucene. There's also Scala link, Scala link to C, which basically allow you to work with the C code in Scala using foreign function memory API, and the Closure foreign function interface are two projects that aren't part of Java ecosystem, but they benefit from Java and the JDK becoming more and more powerful technology, especially backed up with the foreign function memory APIs and vector APIs. Less known Java project, but widely used OpenGL framework is now available for Java developers as well. It's called Panama GL. You can find it on the GitHub. Also, if you have worked with the data science and neural network model training, you probably know what the Onyx runtime is. So it's a C++ library with the C interface, which is available for different platforms based on your system configuration. Either you have a GPU or not. And for now, you have a Linux on the NVIDIA GPU Java library available for use. And the most interesting one is JExtract. JExtract was built using JExtract. At the very beginning of the Project Panama, when the JExtract didn't exist, but the foreign function API was already there. There was a need to implement the access to this CLang library, which is a part of the LLVM project, which if you have ever wondered what that is, the CLang library gives you an access to C code in the form of I wouldn't say like a reflection, but that library can parse the code and give you native symbols that was used by JExtract to generate Java methods for the particular library you are asking it to create bindings for. And then when the JExtract was ready, it was used to create an APIs for the JExtract by substituting the handwritten code with the new one, which is auto-generated, and then the further release cycles will also involve JExtract for JExtract, as long as the JExtract will use a newer version of the CLang library. It's all sound quite interesting and indeed entertaining working with the native code, but I had to admit that the world isn't that bright and sunny as we expect it to be. Unfortunately, Project Panama can only work with C++ indirectly through a procedure also known as type degrading. So for instance, in C++, you can have a class, you can have inline methods, but in C, you only have structs, functions that work with the structs through pointers and the native types only. So instead of vectors in C, you get arrays, and of course, note C++ templates in C. So more disadvantages than benefits. Another type and yet most powerful solution that is built around unassociated C pointers, where the C allow you to whereas C++ allow to construct a pointer that doesn't have a type, or also called broad type, and which is the encapsulated memory segment storing a pointer to a variable of some type. So in this kind of a technique allow you to create a C API that will be allowed to be accessed through different function memory APIs, and JExtract will pick that up in order to create the Java bindings for it. And this kind of a technique allow you to create just an associated pointer. And that pointer is kind of interesting because it can represent whatever variable that is. That could be a class, that could be a template, and etc. And that allow you to work with that piece of memory inside of Java by basically passing it back and forth between Java and C code that will reconstruct a C++ class from the class instance from that pointer, and then invoke a method. This is one of a technique that being used by one of the popular projects that generate Java bindings for C++ code. You probably know what I'm talking about. So, and that kind of a procedure can be used to reconstruct the same type once there is a need to get back to the C++ class instance and in its APIs. So stepping away from C++ type with a broad pointer that is recognized by C and Java, it gives more flexibility to actually make Java code talk to C++ code without type degrading nor any other converting leading to a poorly performing code accompanied by an ugly C code. So you see that if you're going to go back to the type degrading, it means that if you're working with C++ code and you're working with the classes, with all those code that is very specific to C++, the JExtract won't be able to read that code because the way a ceiling library parses the C++ code isn't the same way, it isn't the same what you get for C code. And then in order to make your Java talk to C++, you need to create basically a layer between a JVM and C++ code that will basically be a pure pure C types, including functions, structs, and etc., which means the degrading will cause the performance issues, especially, and it will cause some developer pain because you need to, in some way, to degrade a class to a structure with its private fields, with its methods, and some of them can be templated, which will be like very painful for C because there is no direct translation between templates to see what. But still, such approach require to create. So if you're not doing the type degrading, you're doing unassociated pointers. You're using the unassociated pointer concept that allow you to transform C++ classes to C and then pass it to JVM because it's just a memory pointer. But you see, it's still required to create a wrapper that will basically either create an associated pointer or recast it back to a class instance. And it may take some time, but for now, that's kind of the only way to make it possible to make the JVM talk to the C++ code. Well, it's doable. I have done a few projects using that, and it actually worked, and even in a better way than type degrading. So I'm not going to talk about other solutions like writing all code in C and let the Java just use a very thing, into a very explicit interface to talk that code. And basically we'll run it as we had the same approach with the JNI, whereas the most code is being done in C, while Java part is very, very thin in terms of the amount of code necessary to be written in order to make the native code execution possible. But taking all these techniques into account, you see that indirect C++ access code, the access to the C++ code isn't really a problem of Project Panama, but rather a problem of the LLVM C-Lang library that offer a poor interface for the C++ code. No matter what kind of a code it compiles, there isn't a such thing as an intermediate state between intermediate C code state, but only a meshing code. So if the LLVM or any other tools can turn C++ code into C, that would be a game changer to Java ecosystem, because as you know, or may have seen, most Java libraries nowadays, like for the artificial intelligence or machine learning, compute vision, and etc., are written in C++. Even like the most popular OpenCV library, sometime in the past was written with C code, but in order to evolve, they had to move forward to C++ by discontinuing support for C APIs. And those libraries are written with C++ and have deprecated C APIs very long time ago. So, but some of the libraries still provide you the interface to the C APIs, like Onyx runtime, for instance. So, and the tool that will be able to compile C++ code into C code instead of the meshing code directly will help the whole Java ecosystem to benefit from solutions written in C++ that cannot be directly exported to Java code using the JExtract. So you see, the Project Panama is kind of it's a huge thing for the JVM. First, it gives you an access to native code, which is way different from what it was before with the GNI, but giving you the access to the APIs of a linker, of a memory, the symbol lookup. It gives you a way to describe the function you like to invoke using the function descriptor. Also gives you a way better interface for working with native memory using memory session, segment allocators, or arenas. Which is way more better than, for instance, working with a combination of malloc and free C functions, because you had to do this explicitly. But in Java, you can start the session within the try with resources block, click code block, and then the session will be closed. Memory will be freed back, reclaimed back to the operating system. But also, one of the parts of the Project Panama is vector APIs, which probably would be a game changer to those of you who just use C2 compiler to compile your Java code, because that will make the JVM work even better than it was before the vectors APIs. But obviously, the vector API will be a new opportunity for pure implementation for Java libraries that haven't existed before. For instance, those ones when you need to work with either audio or let's say the audio or video, that often, if you have worked with this, you know that you're going to use FFmpeg stack for that. So now we have the opportunity to do the same with Java by utilizing vectors intrinsics that are available inside of your CPUs, and then provided you either through C++ interface provided by Intel, AMD, or ARM. But if you're doing a pure Java code, you're obviously having access to the vectors APIs, which now still in incubating form, but it's kind of rock solid and gives a very good performance numbers nowadays, even before it will reach the so if you haven't worked with that, I highly recommend to go and try that right now, because once it will become standard feature, that will be the time you will have to already move to new features rather than start experimenting with that. I think that's it for today. We're a bit off time, hopefully not for that long. I hope you really enjoyed this talk. I know it's kind of interesting it's kind of a complicated for people who have not worked with the native code, but obviously at some point of your career, eventually you will get back from Java to C or C++. That's just inevitable stuff.
Fantastic. Thank you so much, Dennis. Does anybody have any questions? I'll just give it a few seconds in case anybody's typing anything in the chat. That's always a good shout. Okay, I will take that as a no questions at this point. So all that is left for me to say is thank you so much, Dennis, for coming and sharing some of what you know. That was really fascinating for us. Yep, great talk. Thanks has gone in the chat already.
Thank you, Craig.
And thank you, everybody, for joining us this evening. It's been great to see you. I really look forward to seeing you at a future LJC event. But just to let you know as well, if you didn't know or you haven't booked yet, our LJC Unconference is happening on the 5th of December in London. So please do have a look at that and come and book and join us. Hello from Manchester Jug. Yay, thanks, Craig. It's great to have you here. So yeah, if you want to come and join us at the LJC Unconference, you're more than welcome. Please do book your tickets because we do have limited spaces now. But thank you again so much, Dennis, for coming and sharing with us.
Thank you so much. Thanks for having me here.
You are so welcome, and we'd love to have you back sometime. That would be great. And thank you everybody for joining us, and I hope you have a really great rest of your evening. Take care, and I'll see you soon. Thank you.
Yeah.
Bye.